Okay, so welcome back. So we continue with our discussion on ferromagnetism, the Ising model, where we had discussed the Ising Hamiltonian and what it does in the previous class. So basically, if a spin is pointing up, it is trying to pull uh, its neighboring magnetic moments or spins to point in the same direction, and that if neighboring spins point in the same direction, then there is a negative energy cost, means the energy is reduced. On the other hand, if all spins point in the same direction, that's just one microstate. So at any finite temperature, a few spins will try to point in the opposite direction, basically to reduce the free energy, because if there are more number of microstates being accessed, then F being the free energy equal to U being the internal energy minus Ts, T being the temperature and S being the entropy, the average number of microstates being accessed. So basically at any finite temperature, the system will try to take more energy from the bath and access larger number of microstates, and the free energy minimization is decided by the minimization of U and the maximization, I mean relative maximization, because there's this minus Ts. So these two terms compete with each other and decide what is the average amount of energy that the system will take from the environment to minimize its free energy, right? So that's the broad physics that's going to happen. Today we're going to discuss more of the mathematics. I hope some of the physics has been discussed in the previous class. Whatever I am going to discuss thereafter follows Rice section 10.7, right? So the Hamiltonian for a particular spin can be written as the Lagrange factor, the magnetic moment into an externally applied magnetic field into spin. Suppose the B is pointing in the Z direction, and so, I mean, in the Ising model, it can take two spin states up and down, but we'll be doing the calculation for the general J, where J can take more values, right? And a special case for the Ising model is when it can point only up and down, right? And this part is the Ising Hamiltonian, where we are again following the Rice convention in writing the exchange energy. So this is called the exchange interaction, the interaction between neighboring spins. That's they're interacting, and minus 2J Ising, just to remind you, Ising, J dash Ising is the convention we are following. And these spins can take plus half and minus half values, right? And each spin is interacting with all its neighbors. And this Hamiltonian, if you sum over all particles, all the magnetic moments that they are there in the lattice, then you'll get the total Hamiltonian of the system. And the convention is such, with the choice of this factor 2 and the values that SIZ can take and SJZ can take, which is half and minus half, that overcounting is accounted for. So the basic mean field, so basically each spin is interacting with its neighbors, and some of the neighbors can be up and some of the neighbors can be down, and different spins can have different numbers of spins, neighboring spins pointing up and down, right? So suppose this is one spin. So it could have two neighboring ups and two neighboring downs, whereas some other spin could have three neighboring ups and one neighboring down. And some other spin could have three neighbors which are pointing down and one which is pointing up. right? So ideally, if I had to calculate the partition function, one has to sum over all possible microstates which is possible for the entire system, calculate its energy, and so on and so forth, and that can be done in 2D, but I mean, square lattice. But we are going to discuss the mean field theory, and that's a much more difficult calculation, and in 3D, as of today, you can't do it. So the drastic simplification that is done is basically each spin, each magnetic moment at each lattice site, it's seeing a different, uh, so because of this coupling, it's seeing a different value or different number of neighbors, magnetic neighbors, and this sum could be, you know, this sum could be all four, or it could be two are up and two are down. In that case, it would be so number of two, or sorry, it would be zero. If three are pointing up, one is pointing down. So it could take different values, right? And each moment in the lattice would have different set of values for this, right? Each I would have a different value. But all of that is being replaced. We say that each magnetic moment is seeing an average effect of the different spins, in the sense that it is like saying that each spin is seeing an internal average magnetic field called HM. So here all the fluctuations that the different spins are seeing, that each spin will be seeing a effective different magnetic field that is washed out. Magnetic field due to the spins, neighboring spins, right? Because it's SI. So if you have SI into B instead, and G and mu zero gives you the strength. Instead, you have JIS and SI into sum of neighbors. So in that sense, if you add the G and mu zero, it's like a magnetic field, except that every site was seeing a different magnetic field. That you replace, that every site over the entire lattice is seeing the same magnetic field HM, right? So you're basically writing the effect of all neighbors as a uniform magnetic field that each point in the lattice is seeing, which is HM. So the HI, the Hamiltonian for a particular spin, can be rewritten as, so this term you are writing it as G mu 0 HM into SZ to bring parity with this term. So you're writing the effect. So this term is being written as minus G mu 0 HM, some magnetic field, average magnetic field, whose value we have to find out at the end of the calculation, right? So that we know what is the magnetic interaction, average magnetic interaction that each spin is seeing under different conditions, different temperatures, right? Because J Ising is a system parameter, number of neighbors is a system parameter. What is the maximum value of SI it can take? I mean, of course, Ising it's plus half and minus half, but in general it can be plus J. So all those things are fixed. So when you're changing the system, you're essentially changing for a particular material, you're essentially changing KBT, the thermal fluctuation. And this HM that each site will see will be different. It will be dependent upon temperature. Why will it be dependent upon temperature? Because at higher temperatures, on an average, a larger number of spins can point opposite to, I mean, suppose at the lowest temperature, all spins are pointing down. Just as an example, it could as well be pointing up. But just as an example, suppose all spins are pointing down at T equal to 0. But as soon as you have some finite temperature, you will have some spins which will flip, which will lead the system to access higher energy microstates. And the higher the temperature you fix of the system, a larger number of spins will flip. If a larger number of spins flip, it is going to access even higher number of energy microstates, right? So if at very high temperatures, an equal number of spins on an average will be up and down, right? So the number of spins that neighboring spins that a particular spin sees to point in the same direction actually depends upon kBt. And since Hm is a substitute for the magnetic field which is being created by the neighboring spins, hence Hm will also depend upon kBt, because larger number of spins point down, the effectively the Hm that a particular magnetic moment will see will be closer and closer to zero, because it will cancel out, right? So that's the meaning. So here what I have written is again energy of a particular spin I can be written as G mu 0 B into Hm, the internal field, the Weiss molecular field, if you like, to Sz. In Ising model, Sz can take only plus half and minus half, but in general, I mean, outside the Ising model, I mean, if you have a Ising-like Hamiltonian, the Ising-like Hamiltonian being like this, then in general, a size it can take my values minus s minus j plus 1 dot 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 to plus j, right? Yeah. Now if you have a magnetic moment, non-interacting magnet, so effect of interaction between neighboring spins has been replaced by Hm. So you could see that now you have many of the magnetic moments sitting on a lattice, which is seeing external magnetic field B plus an average internal magnetic field created by Hm. If external magnetic field B is 0, then all that a particular spin on the lattice will see is this Hm, right? So the effect of interaction has been subsumed, it has been absorbed, it has been incorporated by this Hm. And now you can ask, okay, now suppose you have the field B plus Hm and you have a certain temperature C with T, and there are these n spins sitting on a lattice. So this interaction is now like a non-interacting system, paramagnetic, because effect of interaction has been subsumed in Hm. So what is the magnetic moment of the sample? And if you have independent non-interacting spins, I mean, in reality, they are interacting, but you have written it in a way so that the Hamiltonian looks non-interacting, because you can writing it in this manner. Then you can ask what is the average magnetic moment of the sample in a given magnetic field and at a given temperature. And that has been calculated for the paramagnetic case, and it was J into the Brillouin function, right? So you can go back, and it is basically, I've just copied it from the previous slide where we had calculated for the paramagnetic case. And magnetic moment can be basically mu 0 G, if you like. I mean, G mu 0, I mean, whatever gives the magnetic moment, converts spin into magnetic moment, has been absorbed in within this mu 0. You can write a G outside this, into J into the Brillouin function, because this quantity, the Brillouin function is within this blue bracket, is the average spin that the system that each lattice size has on an average, right? So this is like so this is the average. So mu 0 J is the average spin. So J into Brillouin function is this, and if you multiply it by mu 0, you get the magnetic moment. Right? Except that now eta contains B plus Hm, or rather so G beta mu 0 B plus Hm, whereas in the paramagnetic case, one only had the external magnetic field. And yeah, in the absence of any external magnetic field, the magnetic moment seen by the system was 0. So either you talk about zero magnetic field or you talk about infinite temperature, then the magnetic moment was zero. The spin average spin at each lattice size, the average value, ensemble averaged value is 0. It's this angular bracket denote the average value, ensemble averaged value. On an average, what you will measure, which corresponds to the time average, of course. So for the paramagnetic case, you had this formula, but now this B is replaced by B plus HM for the ferromagnetic case, where HM, the origin of HM is the interaction with its neighbors. So each spin is an average magnetic field. Uh, so 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 what I have done here is uh, so if you had n neighbors, right? Then the magnetic, so in turn, this sum, the average magnetization of each spin, and some over nearest neighbors, and each has this value, right? Is then n j Brillouin function of j, function of eta, right? So this spin has 4 neighbors, each has an average spin of this value. So this particle is seeing these 4 neighbors. So this magnetic moment is seeing these 4 neighbors, each of which has an average spin value given by this. So this guy, when you sum over the 4 cases, it becomes NJBG. That's all that is there to it, right? And that has been written as HM, as we discussed. Right? So this term now, again, writing Hamiltonian for a particular spin, is 2J Ising. This is written here. SIZ, like each spin. I'm recording. I'll call you later in half an hour. So, sorry. So this spin is this term, yeah, and the effect, this sum over all neighbors, is now replaced by Nj Brillouin function of J. On the other hand, we had also written this entire term like, I mean, the effect of this had also been written in terms of HM, G mu 0 HM, to bring some symmetry with this term. In that case, cancelling out this SIZ from both, you can write so basically there was a minus sign here and there was a minus sign here. So 2J Ising N Brillouin function of J, function of eta, is equal to G mu 0 HM. So this effect of G mu 0, so these are average spin values, right? Right, and so this is the average spin values. So this would contain things like the magnetic moment. So we are comparing magnetic moments. I mean, yeah. So we are comparing these two equivalent quantities where we have. So if you multiply SIZ at a lattice side, this would give you energy, and similarly, if you multiply SIZ, it will give you energy. This is spin into whatever makes it the energy due to moment interactions. So what was the mean field approximation? Sorry, this should be sum over J, sum over neighbors. So it's SIZ. So this sum of over neighbors, I is interacting with its neighbors. This should be J, I repeat. Sum over J, all its nearest neighbors, is being replaced by n SIZ. This is the mean field approximation. It would have different values at each lattice site. That is being replaced by a mean average value, which each spin SIZ is seeing. Each spin is seeing the same value, which is n times, if there are n neighbors, into a mean magnetic moment. So this is the mean field approximation. This in turn can be written as J into Brillouin function, J of eta, right? Yeah, and the basic message is, by doing this, from going from here to here, you have converted an interacting problem. So interacting problem converted into an effective non-interacting system with the mean field of HM. So that's what has been done. And this is the mean field approximation, the Weiss. It's called the molecular field as well. Going ahead, so that was the background. Now we're up for some algebra. So what we have written is 2J G-izing. This is the magnetic, this is the spin quantum number, which for Ising case should be half and minus half, but I've written it in general following the Rife convention. N number of neighbors into Brillouin function J equal to G mu 0, the Landé factor, into the Bohr magneton into HM. But remember, inside eta, what is eta? It is beta G0 mu 0 B plus HM. Right? It's a Brillouin function, where Brillouin function was this cot hyperbolic function, cos hyperbolic by sine hyperbolic, G plus half eta, cos hyperbolic by sine hyperbolic. So this was Brillouin function. And you have that, and inside that you have HM. On the right hand side of the equation, again you have HM. So this is a transcendental equation. It cannot be like simplified, right? So here we have eta, and here we have HM. So what we do is, we can either write, so here I have written on both sides of the equation, you have HM. On the other hand, you can substitute this HM and write it in terms of eta. And why can you write that? Because eta, basically I'm taking, so this was eta. So this equal to this relationship, and in turn, you can write HM to be eta by beta G mu 0 minus B. And that is exactly what I have done. So here in this equation, so here on both sides of the equation, you have HM, and you can solve it by that. Or what we have done is substitute HM and write it in terms of eta. So on both sides of the equation, now you have eta, and HM goes missing because you have substituted HM in terms of eta and B, right? And then you're writing the Brillouin function. These prefactors, you're putting it in the denominator. You're just putting it in the denominator, taking these terms inside the square brackets, and this relationship becomes Brillouin function equal to kBt. So remember, this looks more like a tan hyperbolic function, the Brillouin function, though it's a sum of two cot hyperbolic function. When you plot it, it looks like a tan hyperbolic function. It doesn't become a tan hyperbolic. It remains Brillouin function, right? But its look becomes like a tan hyperbolic. That's all that I meant. Not that it becomes a tan hyperbolic. Well, actually, it becomes only for when spin equal to half. But anyway, it's this. So now the question is, this relation holds. I mean, you have imposed this relation. You have imposed this relation by saying, oh, I'm going to take a mean field, replace it by HM. We shall assume that the effect of the magnetic fields of the neighbors can be replaced. Effect of the spin of the magnetic moment of the neighbors can be replaced by an HM. and considered it to be a non-interacting system in the presence of a mean field of HM and B, and say that, oh, you have calculated some average spin of the system and demanded that. You have demanded it as an approximation. But does it hold? Does this relation hold? You have demanded this relation. But are there conditions where you can self-consistently calculate a unique value of eta? So we are actually looking for a solution, if any, for a particular value of eta. So our aim is to solve for that eta. So this is a cot hyperbolic function. The right hand side of the equation looks more like a straight line. Is there any particular value of eta, or correspondingly, if you wanted to work with this, do you have a value of HM for which this relationship is satisfied? Because we have demanded this, right? Under certain conditions, is this condition satisfied? And that is the solution. For a particular value of eta, this and this are equal or not. We are looking for a solution. We are solving for eta. So when b equal to 0, so note on the right hand side of the equation, there's an external magnetic field B setting in, and if b equal to 0, this relation will become Brillouin function equal to, so the left hand side of the equation, that's kbt by 2njj dash into eta. Okay. And eta simultaneously is from its definition, because it basically comes here. We have defined g mu 0, right? So it's from here. We can also write eta to be g mu 0 b plus hm by kbt. And of course, if b is 0, this will be 0. Then you have g mu 0 hm by kbt. Now, how do we solve for it? So what we do is plot the left hand side of the equation. Let's call that y. And the right hand side of the equation. When b equal to 0, this term will be missing. You will just have this. So y dash equal to right hand side of the equation. Let's plot this. And if they intersect for a particular value of eta, then this equality will hold only for that value of eta, and that will be the solution to this equation. Right? So we are looking for a solution where we demand this equality, and we are checking if there are. So at eta equal to 0, so this, if you look carefully, so this Brillouin function is this green line. It looks like this. You can plot it in the software of your choice for a particular value of j, and so on and so forth, j-izing and so on and so forth. On the right hand side of the equation, you have an equation which looks like y dash. The right hand side of the equation looks like mx minus a, where x is eta actually. So this is x, if you like. This is the slope mx, and this is something like a, right? If you put it, if you take these terms inside the square bracket, so that's an equation of a straight line. And if b equal to 0, then equal to b means the magnetic field equal to 0, then a equal to 0. Then you have a line y equal to mx, which is passing through the origin, right? And provided the slope of this line, what is the slope? It's this no, not this quantity. This quantity is lower here. So here it's lower, then it will intersect at a finite value of eta, at a finite value of hm, right? On the other hand, if the line went like this, suppose the line went like this, then the only solution is at eta equal to 0. What is eta? That is this. right? So eta equal to 0 means kbt equal to infinity. That's the only place that they two intersect. But so the slope of the right hand side, if the slope of the right hand side of the equation, what is the slope of the right hand side of the equation? It's kbt, right? So if kbt is 0, slope is 0. If kbt is infinity, slope is infinity. N, J dash, number of neighbors, the Ising interaction, J will be for the Ising model half, right? But in general, it can be more. So basically, if you note, for small values of eta, the Brillouin function, so here it behaves, the Brillouin function behaves like 1/3 j plus 1 eta at eta equal to 0. Here, of course, it looks like a tan hyperbolic, but here it behaves like a nearly a straight line for close to eta. Then we can compare the slopes, because if the slope of this line is greater than the slope of this line, then it intersects only at eta equal to 0. That's the only point where this relationship is satisfied. On the other hand, if the slope of this line, the slope of this line is this one, is lower than this quantity, the Brillouin function, yeah, because we simplified it, so the left hand side of the equation is the Brillouin function, the right hand side is this. Now, if the slope of this is lower than the slope of the Brillouin function at eta equal to 0, then they not only meet at the origin, but this line will also intersect at some non-zero value of eta, which will give you a non-zero value of hm in turn, even when b equal to 0, right? So this line passes through the origin only when b is equal to 0, and you still have a finite value of eta, right? Which means you have a finite value of hm. If hm equal to 0, eta equal to 0. If eta was equal to 0 was the only solution, that means hm equal to 0 was the only solution. What is hm? It's the effective magnetic moment that a particular spin is seeing from its neighbors. That means if eta equal to 0 and hm equal to 0, that means it's seeing a zero magnetic moment due to its neighbors. There's no net magnetic moment that any spin is seeing due to its neighbors in the absence of B. That's what it means, right? So just repeating, the slope of Brillouin function is 1/3 j plus 1 for eta equal to 0, not in general. And slope of y dash, the right hand side of the equation of kbt equal to is this. For slope of the Brillouin function to be less, so y was this. So when the slope of y dash, this line, is less than the slope of y, which is case like this, then you have some spontaneous magnetization. You have a solution at a finite value of eta. You have a case of finite internal magnetic field hm. On the other hand, if this slope of y dash, right, was more than the slope, then you have the only solution is that eta equal to 0. Means Sm is always equal to 0 at high temperatures. Because slope of y dash is decided by kbt. And the critical point where they just touch, where you start showing a finite value of hm, the critical point between these two regimes is when these two slopes are equal. And when you equate these two slopes, the value of kBTC, unit of energy, that you get is 2n j plus dash. All that I have done is basically rearrange terms. I've put this equal to and written kbt equal to. So kBTC equal to, because now we're, so this is 2n j plus 1 J Ising, right, by 3. So this is your critical point as per the mean field approximation of the Ising model. The exact TC you can get out only by getting the partition function and doing the exact calculation. Here you have done a mean field calculation. The mean field critical point is given by 2n number of neighbors increases, critical point, the critical temperature increases, J increases, critical temperature increases, the energy of interaction increases, critical temperature increases, right? On both sides of the equation you have units of energy. So when B, the external magnetic field, is present, so this was when there was no external magnetic field present, right? Now, if an external magnetic field is present, then you would have this extra term as well, right? And eta now would be this relationship, right? It will have something like this, right? But if you look at it, if you calculate what is Tc, so Tc is this quantity, this entire quantity by Kb. So when you have a magnetic field, eta can be written as, this is the same thing except it's it can be written by T by Tc, eta minus G mu 0 B by Kbt, right? So which in turn, I mean, you can take this Tc here and rewrite the equation like eta T into, you bring this temperature within the brackets, you push it inside the brackets and simplify. You'll get essentially eta equal to G mu 0 B Kb T minus Tc, right? So I have rewritten that. So then the magnetic moment of the entire sample, is N into G mu 0 into the mean magnetic moment, which in turn is J. So this term can be written as J Bj, Brillouin function of J into eta. And for eta less than 1, right, for close to 0, where eta is small, that is Kbt is high, one is simplifying only under these conditions. One is simplifying the Brillouin function and writing it as J plus 1 by 3 into eta, right? And thereby you get the value of the magnetic moment inside the sample. And eta, remember, has both B and Hm because B is non-zero, right? Okay, so here, so if you write, where did the expression for eta go? Eta is this, G mu 0 B plus Hm by Kbt. So substitute that here, right? So substitute eta because eta is G mu 0 B plus M, and now you have B non equal to 0. If B was equal to 0, then this B will be equal to 0, it will be. But you can calculate the susceptibility as the change of magnetic moment with del B. And if you take the derivative, and if you take the derivative, right, so this is the magnetic moment, and if you take the derivative, then you would get this prefactor upon 1 by T minus Tc. And why will you get that? Okay, so you're replacing this eta, you rather than use this term, you're using this term which has an explicit temperature dependence. So the effect of Hm has been incorporated in this Tc, right? So this effect of Hm has been incorporated in this Tc here, because so you're writing it's like this and so on and so forth. So HM, so here there was HM and that has been replaced by eta by this thing. So effect of HM has been replaced by this. You are right. You're taking actually a derivative of the, so when you have this eta, instead of this term, you use this one, right? Because yeah, B can also affect SM actually, because it a magnetic, if you have an external magnetic field, a larger number of spins will point in the same direction of magnetic field, which in turn will affect HM. So you don't want to work with an expression which has HM here, but you would rather work with this expression G mu 0 B. And now you are taking to calculate chi a derivative with respect to B as B tends to 0. So chi is defined as B tends to 0. And then you would get this prefactor. So you have to substitute this here, and you take a derivative with respect to B, and you will get n g square mu 0 square j into j plus 1 upon 3 kb upon 1 minus Tc, T minus Tc, which means as temperature approaches Tc, the chi goes to infinity or close to infinity, right? Which was also seen experimentally when I had shown the previous graphs. So I'll just remind you, I think it was around page 20. Yeah, this is the right graph. So you remember at a particular value of Tc, 1 by chi was 0, which means chi was going to infinity, right? And we have got that also. But having said that, let me tell you that the way, so this dependence upon 1 upon T minus Tc, yes, it's showing the infinity, but we have used a mean field approximation. There are various other details which actually don't exactly the nature of the curve, the way it goes to Tc, the so-called critical exponents and so on and so forth, the behavior of chi and m, the way it goes down, what is seen experimentally. This mean field approximation shows a good description of the behavior, but not a perfect description, because we took this drastic assumption of this mean field theory, right? So there are more sophisticated, better approximate methods which shows a better match with the experimental data. Having said that, having solved this problem in this manner, this chi goes as 1 by T minus Tc. That is what was seen initially experimentally, without going into the details. That's the broad behavior. And this also is called the Curie-Weiss's law. Okay. This was called the Curie-Weiss's law. This is the behavior at low eta. And of course, at high eta, it shows the so what you could do is plot. You could plot for various values of temperature, what value of solution do you get, right? And you see, you have a reasonable behavior. This is the experimental data. Here there are deviations as T approaches Tc. This is the magnetization curve, but it is a reasonable description to what is seen in experiments. Not perfect, but reasonable. So what has been done here? Your various values of eta has been calculated at different values of temperature, the solid line, and you try to calculate the mean magnetization from the value of eta, right? So we have solved for eta, and just to go back here, this is the magnetization in general here. So if you know the value, so what is the value of eta, for that you substitute here and calculate the average magnetization where this is. n to n, if there are n atoms or n magnetic moments. For one particle, G mu 0 J Brillouin function of J is the mean magnetic moment per particle, and this can be written as this quantity can be written as J plus 1 by 3 into eta only at as eta approaches 0, when eta is much less than 1 but KBT is very high. And new susceptibility shows this behavior. Magnetization shows the behavior in that it drops. So with that comes end to the mean field solution to the Ising model, where even in the absence of an external magnetic moment, you see a spontaneous value of eta or Hm, which corresponds to large number, each magnetic moment seeing a finite value of magnetic moment due to its neighbors. So there's a spontaneous magnetization which is produced at each lattice site, and each lattice point is seeing an average magnetic field, which is an average due to the fluctuations of its neighbors, a finite value, a non-zero value. In the absence of an external magnetic field, each is seeing a finite magnetic moment due to its neighbors, and that in turn is that there is a finite magnetic moment over the entire sample given by this value. This has a non-zero value. As a consequence, spontaneous magnetization of the sample has a non-zero value. There is spontaneous magnetization in the system at finite temperatures due to interaction with its neighbors, which is ferromagnetism. Okay, so just think about it, go to the lecture once more. There's no point in me repeating the same thing over and over again. So I'll just stop recording here.